Hello, good morning. Welcome to another session on pointers. I am Dr. Suresh from Infosys. So in the last few sessions, we have looked into few topics in pointers in C. So specifically, we spent enough time on pointers and addresses. Then we figured out what a pointer is, what an address is, how do you dereference the pointers, how do you have pointer to pointers, pointers and functions, pointers and arrays, and address arithmetic. So today we will look at the character pointers or pointers to characters and functions, and the initialization of pointer arrays and the dynamic allocation methods in C. So before we actually do that, let's quickly try to have a recap of the things that we have done. So to start, we'll see some of the confusing declaration in pointers, and then we'll see some hands-on. So integer star x is the simplest declaration that we have seen. That means x is a pointer to an int data type. Int star x10 declares x as an array of 10 of pointer to integer data type. Integer star of x of 10 declares an array of 10 of pointer to integer data type. Integer star star x, where x is a pointer to an integer data type, also called as double pointers. Integer star x10 declares x as a pointer to an array of 10 of integer data type. Integer star function declares function is as a function returning an integer pointer. So the rest of the things we can see it later. So before we concluded the previous session, we looked at the pointer arithmetic. Let us try to sum it up by taking a small hands-on example. So I have a small C file. So let's quickly go through the source code, and then we'll see the output of that, and try to understand what or how does pointer arithmetic is different from normal arithmetic. Sometime in the previous session we did mention that pointers in a sense are integer data types, specifically unsigned integer data types, but their arithmetic is quite different. So this particular example will summarize all the things that we have seen so far. So we'll not play around with too many variables. I have two variables, integer I and j. J I have initialized to 10. Integers star ip. Ip is a pointer to an integer. Ip is equal to %i. So now ip is pointing to I. That means ip has the address of I. And then I have character C and I have character pointer PC. Then I have an array integer a of 10, and I have three pointers IA1, IA2, IA3. So all of them point to integer data types. So let's quickly see we'll quickly write some print statements. So what in the first print we'll see size of C. So C written in here is basically a constant character C. So then I have a tab there, and size of character, okay, and then size of character star, character pointer, and this is what I print: size of C, size of character, size of PC. So then I have size of 100 is an integer constant, size of int, then size of long integer, and then size of short integer. So that's exactly what I specify here. Then I have with respect to float. So let me get the size of a floating point constant, and the size of float data type, size of double data type, and this is exactly what I write here. okay, and then I print a blank line. So, what I have done in this 3 set of lines, a set of 3 printf lines, is I am trying to capture the size of character, the size of integer, and the size of floating point numbers and the respective pointers. We also saw in the last session that pointers and arrays have a very strong relationship. So, though user uses an array representation, internally the C compiler interprets as a pointer representation. So, we have declared A as an integer. So, A is an array and J is an integer data type. So, if I try to print the size of A, remember A is inherently a pointer to integer, okay, but it is a pointer to a block of integers. In this case, it is 10 integers. Let us look at one element A of 0. What is the size of integer? Each element in array A is integer, and then I will see what is J. J is an integer. Let us see the size of that. Okay. So, then what I do is I open up a for loop. See, I start the for loop with 0 go up to 9 with an increment of 2. So, what I have done is I have used the first statement using the normal array representation, whereas I access the subsequent element using the pointer arithmetic. Okay. So, remember A is a pointer and then I is the index of this, and I add 1 to that, okay, and then here. So, basically this statement is going to assign 0, 20, 40 to alternate indices. So, this particular statement is going to assign 5, 25, 45, 65 to alternate indices. So, then I use the pointer arithmetic to print the values in the array, okay, and then I will see the different ways of accessing the elements using pointer arithmetic, okay. And then I use exclusively these 2 pointers to point to the first, see IA1 is a pointer, now it points to the first element, this points to the last element, and I will access the array, okay, and I will also do some pointer arithmetic like this IA2 minus IA1, okay. So, anyway, because I have inserted appropriate messages, this should not be difficult for me to understand when I get the output of this. So, I have already compiled this, let me execute that. So, this is what I get. So, this is the first set of 3 print statements. So, size of C happens to be 4, okay. So, there is some do not get too much confusion here. So, most of the C compilers are machine dependent. So, they try to optimize the memory accesses based on the architecture of the processor. So, in this case the C compiler decided to allocate 4 bytes to the constant C, though it requires only 1 byte, whereas if you see size of character, it is still 1 byte. Okay. Size of character star, which we discussed, that it is of integer type, unsigned integer specifically, is of 4. So, size of 100, which is integer constant, is 4 bytes, size of int is 4 bytes, size of long is 4 bytes, size of short is 2 bytes. This is with respect to this compiler running on this particular machine. So, size of 2.3 is a floating point number, it gives 8 bytes, size of float is 4 bytes, size of double is 8, but that means by default I am getting a double precision number for this constant. So, that gives us an idea of the different sizes of the data types. A of 10 is an array, we have declared it, and J is an integer. So, if I try to get the size of A, I get 40, because there are 10 integers there. So, 10 into 4 is the size of int. So, I get 40 bytes there, whereas if I get the size of only one element in the array, I get 4 bytes, which is the size of an integer. So, size of J happens to be an integer, so it is 4 bytes. So, the elements of array, you remember I used both the array representation as well as the pointer arithmetic to assign alternate numbers. So, this is the loop index and I added 5 to that. So, the subsequent element gets 5 and then this gets actually 20, 2 into 10, okay, this gets 2 into 10 plus 5 and so on. So, pointers, so all these elements 0, 20, 40 have been assigned using simple array representation, whereas the alternate numbers are assigned using pointers. So, similarly, a of 0 is equal to 0, this is one way of accessing the element. Star a is equal to 0, content of pointer a. So, content of a plus 1 happens to be 5, content of a of 1 happens to be 5. So, these are alternate ways of. So, here is where we can appreciate the pointer arithmetic. A is an integer which is a pointer pointing to the first element, that means a happens to be the address of a of 0, but if you add 1 to that, actually 4 is getting added because 4 happens to be the size of integer. Similarly, here if I am adding 2, what is getting added? 2 multiplied by 4. So, a plus 8 is happening here. So, I get the address of the second element of the array, and that is what I get. Okay. So, there is a scaling in terms of pointer arithmetic whenever you do arithmetic operation. So, this you have to be very clear, and that is further kind of explained in this output. Okay. So, I is equal to 0, which is a loop index. So, IA1 happens to be the address of the first element of the array. So, IA plus I happens to be the address of the first element of the array. If you remember, a of 0 is 0, I am getting 0 here. So, if you look at the pointer itself, this is the pointer. Okay. So, this is the pointer value. Okay. This is the pointer value. Okay. So, IA1 plus I is equal to 0. So, if you see here, IA1 plus I, so I happens to be 1. Now, so this has to be added with 1, but you see the value 4 is getting added. So, this entire table say kind of demonstrates the pointer arithmetic. Okay. So, array A printed from last to the first using IA2 minus I. So, IA2 happens to be the pointer and it is pointing to the last element in the array. So, IA2 minus 0 will give me the last element. So, this is 85 and I do that in the reverse order. Okay. So, I can access the array from first to last or last to first using pointer arithmetic. Okay. So, lastly I have IA1 assigned to the address of 0, address of a of 0, I get this, and IA2 I have assigned it to the address of the last element, this happens to be that. Now, if I subtract these two, see it is a big number, okay, basically it is 40. So, what I get is actually 9. Okay. So, again there is a reverse scaling that is happening. So, this particular examples explains all the nuances of pointers and pointer arithmetic. So, we will come back to the main. So, there is a lot of fun that we can see in pointer arithmetic or pointers in C. So, characters or strings in C is basically an array of characters. So, let us have say character S of 6. So, this the sequence of assignments that I have S of 0 to S of I is a straightforward assignment to the character elements in the array. So, I have basically hello assigned to this H E L L O and then a slash 0, because all strings in C should terminate with a slash 0 character. So, end of string character. So, if I print that, what I get is hello. So, one of the easiest way of remembering this nuance of pointer arithmetic is if I have expression 1 within square brackets expression 2 in C is just a syntactic sugar for contents of expression 1 plus expression 2. That means, expression 2 and expression 1 are treated as integers. If it is a pointer, suitable scaling is applied and the contents of that is fetched. Okay. So, let us explore that here. Let us look at the different ways in which I can access the array element. So, character S of 6 similar to the previous one, star S happens to be accessing the first element of the character array. I assign it to H, then I use S plus 1. So, S is a pointer, 1 is an integer, appropriate arithmetic is made, star of that I assign it to E, 2 of S, see S of, instead of S of 2 I can write 2 of S, it does the same, Okay. Similarly, 3 of s is also assigned to L, then star of s plus 4 is equal to 0, sorry, O, and the last character happens to be /0. If I print the string now, I still get hello. So, look at the different ways of accessing the array element. Okay. So, the more you understand this, the more expressive you can be as a programmer. Okay. Now, let us look at the first topic in today's contents, character pointers and functions. A quick recap of some of the basics of characters that you have already seen in some of the previous sessions. Character is a 1 byte data type capable of holding a character. So, by and large the ASCII code is used to represent characters. To a large extent, it is treated as an integer type. Okay. So, usually unsigned. So, characters inherently means 1 byte unsigned integer. So, it can be used in arithmetic expression just like you use integers. You can add, subtract, multiply, divide, but there is no scaling that happens because this is not a pointer data type. So, now you have characters. These are some of the characters. So, what you should remember is capital A to Z and lowercase a to Z and digits 0 to 9 are all in order. That means ASCII A to ASCII Z is a linear sequence. Similarly, ASCII small a to Z is a linear sequence, similarity is 0 to 9. So, that arithmetic can be done very comfortably. So, a string in C is a character array ending with /0. So, these are different ways of declaring or say declaring space to hold strings. Character S256 is a statically declared array of characters of 256 characters. So, here you have character, you have character T, but you have an assignment here. So, you do not write a /0 explicitly here, because the moment you put the double quotes, the /0 is automatically inserted by the compiler. Okay. And this is the third way, or probably the new way of assigning string to a variable. So, this is u is basically a pointer, it is a pointer to character data type. So, this is another string. So, again here the /0 is inserted automatically by the compiler. Okay. So, these are three different ways of storing or declaring space for storing a string. Okay. String constants are usually written in double quotes, and within the double quotes you can have any character including double quote, single quote, reverse slash, etc. You can refer to the string data type in your earlier class. Okay. So, let us now just focus on the new way of assigning strings. So, character star u. So, the string that this is another string. So, this assigns a pointer to the character array. So, u now becomes a pointer to the character array whose size is the length of the string plus 1, that 1 basically is required to store the /0. So, if I access u of 0 I get t, if I access u of 1 I get h, similarly if I access u of 22 I get the exclamation sign. So, both are equivalent. So, most string manipulation functions that you have seen is done through functions which are defined in string.h. String functions depend generally the final /0. If you want to count the number of characters in the string, so you should go on counting until you get a /0. So, the /0 is a very important element in the character array. So, examples string len character star s, you see you send the pointer to the character array, you do not send the character array, it returns the length of the string excluding the /0. So, character star string copy, you send two pointers s and ct, both are character pointers. So, s is a pointer to character array, ct is also a pointer to character array, both are supposed to hold strings sending with /0. So, copy string ct. So, whatever string that this is pointing to is copied to this s. The only condition is s must be big enough to hold the contents of ct. If ct is smaller, it is all right, but if ct is bigger, this returns an error condition, because you cannot copy all the characters pointed by ct into the storage that is pointed by s, or the character array pointed by s, because it cannot hold all of them. So, if you do not capture this /0, the problem becomes it does not become a string, you do not know what is I mean where does the string ends, and there are a lot of problems that could occur. Now, the question you may be in a dilemma. So, we in fact answered some of these questions or some of the questions in this dilemma earlier as well when we discussed pointers and functions. So, how you can enable functions to return multiple data. So, we will re-emphasize that in this case. So, if strings are array of characters and if arrays cannot be returned from functions, then how can we manipulate variable length strings and pass them around in our programs? Okay. So, the answer is use storage allocated in the heap. So, we will not discuss the heap at this point of time. So, but very soon we will discuss what is this heap. Let us quickly look at the character arrays. We will take one simple example or maybe couple of simple examples before we actually do address the allocation of space on the heap. So, quickly there is a function called match. It takes two arrays. So, basically two character arrays. So, character star s and character star t. So, basically what it does is it goes on comparing character by character of string s and t and returns the number of characters that it matched. So, the moment there is a mismatch, the counting stops. So, it returns the number of characters from the left of the string that gets matched with the other string until you get two characters which are not the same. So, the logic is simple. You start with count as 0 and then you have this two pointers, and I use that to check contents of s, contents of t, and if they are equal, I add I increment count, I increment s, I increment t, and I return count. The moment this while loop comes out, count would have counted the number of characters that has matched until the first mismatch. Okay. So, if I have to call this function, a very simple thing, s1 of 6 is hello, s2 of 6 is ho ho ho. Then I call match using different techniques. So, in the first I call match with s1 and s2. That means I send both of them starting from the first character. So, can you quickly guess if you see h and h matches, e and o does not match, so it should return 1. Okay, so it should return 1. Okay, so that is what you get here. So, now if I write match of s2 and s2 plus 2, let us see what happens. S2 is what? S2 is a pointer to a character array. So, the S2 is basically holding the address of S2 of 0. Okay, that means it is pointing to H. What is S2 plus 2? Okay, so S2 plus 2 is basically it is holding the address of O. Sorry, address of the third element 0, 1 and 2. Okay. So, what has now been passed is a pointer to HOH and a pointer to HOH. So, how many characters get matched? H matches with this H, O matches with this O, H matches with this H, and you hit a /0. Okay. So, the match is basically 3. So, then I use the pointers of S2 of 1, that means it is nothing but S2, pointer to this O, and I have this 3. So, that is 1, 2, 3. So, OH, and that is it. So, the match is 2. So, if you look at this block of statements, ampersand S2 of 1, ampersand of star of S2 plus 1, S2 plus 1, they are all one and the same. So, all these basically refers or returns or is referring to the pointer to the first element in the array, in the character array S2, that means it is pointing to O. Okay. So, we can use the pointer arithmetic to condense the code that we have written for match. If you see here, there is a while loop and there are 3 increments. I can avoid all those things by doing this. So, I have a local variable OS which points to the address of S, address of character array pointed by S. Then I will do just this star S plus plus star T plus plus. Okay, because the way in which I have used the post increment, so while returning I have to manipulate that appropriately. So, now S is basically pointing to the character to the second character after the mismatch. Okay, that is exactly why you have to knock off this -1 from this, because OS is pointing to the first address, S points to the address of the character which has mismatched plus 1. So, that is why you have to return subtract 1 from it before you return the value. So, what we have done so far is function arguments and pointers, and then you have arrays and pointers, and we have recapped on pointer arithmetic. So, now we will come to probably the most important concept in pointers. So, whatever that we have done so far is to make you comfortable with understanding what a pointer is, what is pointer arithmetic, and how do you manipulate pointers, how do you access the contents using a pointer, and so on, and its ability to play a significant role in function calls. So, what we discuss now is actually the real power of pointers. Okay. You remember when I discussed the program layout, the application program layout in the memory, I did talk about how the program gets when it becomes active, when it actually runs on the computer, how the memory is allocated. So, as soon after that I did mention that pointers are addresses pointing to addresses in heap. This particular session or this particular topic basically further deep dives into it. Okay. So, now to just make you more clear, let us have a recap of the application program memory, and then we will see the limitations of stack, and then we will discuss what is heap, and before we get into actually the dynamic memory allocation. You remember that we had this layout discussed probably in the very first session of pointers. When a program gets compiled, so these are the things which gets defined. So, the bottommost 3 regions, the program instruction, that means the code of the program, which is the binary equivalent. Okay. This is basically 1s and 0. This is also called as a text block. You have some static variables. Static variables can be allocated by the compiler. So, these are static variables, and then you have some global variables. So, these 2-3 blocks put together is what we call as permanent storage area. Okay. When your program gets loaded into main memory, this much space has to be provided in the main memory. So, when the program actually starts its execution, main is the first function that gets called. So, as soon as the main function starts executing, it needs a stack, because the local variables of the main function has to be allocated. Okay. So, for that the compiler and the operating system communicate with each other, they have an understanding. So, it will allocate what we call as stack space, the green one, which is basically used for local variables apart from some housekeeping data. So, then you have what we call as free memory, and is also called as heap. It is a huge space that is allocated to the program which is running. So, currently to begin with the heap will be empty, there will be nothing in heap. So, now let us see when the program actually starts executing. Let us not worry too much about the permanent storage area, because there is nothing, everything is statically allocated. So, we should worry more about stacks initially, and then we will see how to use heap. Let us look at a simple example. Okay. There is a main function, there is a function, there are 2 functions that have been defined. So, if you see in the main, okay, as soon as the control gets transferred to the main function, this is allocated. So, all these 5 blocks are allocated. So, we will just focus on stack. So, I have blown up the region of stack. So, basically this is the projection of the stack that we have here. Let us see what happens on the stack. The moment the moment main function is called, so that is what happens. A space is allocated in the stack. So, the compiler knows how much stack is required, because all the local variables is known by the compiler during compile time. So, it allocates the stack space. Okay, and because stack is already allocated by the operating system, so it uses a portion of the stack like this. So, what happens? there is a space for local variable A, there is a space for local variable B, there is a space for local variable total. So, that is what I write A comma B comma total. Then what happens? I call square of sum. What happens now? The stack. So, this is what the boundary here, this block is called stack frame for main function. So, the moment square of sum is called, the control is passed from here to here. Correspondingly, a new stack frame is provided by, the new stack frame is acquired by the program which is running. Again, the size of the stack frame can be predetermined. So, as soon the compiler knows what is the stack size that is required for this function. So, it allocates this. See, apart from the local variables now x, y and z, it will also probably put some information, so that when this function actually returns, it knows that it should return to the statement following square of sum, which is basically the printf statement. Okay. So, now within square of sum there is another call to a function. So, what happens then? Another stack gets created, the local variables of that function gets allocated. Now, we execute return x into x. So, the moment this return statement is executed, that stack goes off. That is why we call the local variables have some scope. As long as the function is executing, you can access those local variables. The moment that function returns, that stack frame goes away from the stack. Okay. And then what happens? It comes here, and then there is a return z, and then the control comes back to main. So, at this point of time, I do not have access to z, I do not have access to this x and this y, neither I have access to this x. The only thing that I can access now is a, b and total. Okay. Now, I have printf statement, which is again a function. So, a printf stack is allocated, and then when the printf actually returns, I come back here. Okay. That is the way in which stack is used. Okay. For any program running on any machine, this stack size is predefined. Okay. So, there is a fixed size stack that is provided by the operating system to the program which is running. Okay. So, if for some reason you go on consume the entire stack, you will get an error called stack overflow. Those of you who have written programs using recursion and maybe have committed some mistake in writing recursion programs, you might have encountered that error which is called as stack overflow. So, stack overflow is nothing but your program while running consumes the whole lot of stack that is provided to you and seeks for some more space on the stack. So, the moment the operating system cannot give a space to the stack, you get an error. Okay. Let us see what is stack memory. It is a fixed size stack which is allocated when a program starts. Primarily, it is the job of the operating system. Stack frames and allocation of space to local variables happens in runtime. We saw from main you got sum of square and then square, and then when square returned, this stack shrunk. When the sum of squares returned, so we lost the stack frame of that. Okay. So, large number of function calls, typically it happens in recursive functions, may result in stack overflow, and generally the program crashes. Large number of variables also result in program crash. So, suppose you invariably declare a large array as a local variable, so you can encounter this. So, all this what primarily says is stack is of fixed size, okay, and if you exceed that, so now very soon we will quickly say figure out that there is a limitation. Okay. So, the total stack size is limited and is dictated by the specification of the operating system. So, if you want to have large arrays or data as local variables, you will be consuming the stack space, which may not be good. So, more space on stack is generally not a good idea. So, stack frame allocation is controlled by program execution. Okay. So, you do not have the user do not have control over it. When the program executes, the stack frames gets allocated. When the program returns, the stack frame is taken away. That means the scope of local variables cannot be changed. So, these are the limitations of stack. Now, the question comes, if I want bigger arrays, if I want big spaces, Okay, so normally program is a collection of functions, and we don't know which function is used for a particular data that has been provided to that particular execution. So we don't know. So that's exactly when the heap comes into play. The size of the heap can vary during the lifetime of program bar application. That means the operating system is, most modern day operating systems are ready to give as much memory as the program wants. That we call it as virtual memory. You will see and study it in detail in a course called operating system sometime later in your course. Okay, so all that you need to know is stack is of limited size, heap is by and large unlimited. Okay, there is always a limit, but it's very big limit. No set of rules is provided for allocation and deallocation of memory on the heap, whereas in the stack it was clearly your program, the way in which your program executions, the stacks was allocated. Okay, so the programmer has full control of allocation and deallocation of space. So basically heap is nothing but a large pool of memory. Okay, we call it as dynamic memory. So again, you should not confuse this heap to the heap, the data structure called heap. I will not discuss anything about the data structure heap, but the heap that we are discussing is, has no relationship with the data structure that you will study later in data structures. Now let us see, we said in this example or in this slide that programmer has full control of allocation and deallocation of space on heap, whereas stack was not under the control of programmer, it was the control of program execution. So there are 4 methods or 4 functions in C which helps you to manipulate the allocation and deallocation of space on heap. Malloc, it is also called as memory allocation, calloc, calculate and allocate, realloc, then free. We will discuss malloc to a great extent because malloc is the most general of these first 3 functions. Calloc and realloc is primarily comes after malloc, and free is also important. We will see the importance of free very soon. So we will discuss more on the first and the last functions, but we will also see what the other 2 functions do. Okay, let us take a simple example before we actually discuss the syntax of the malloc function or the free function. So on the right hand side you have those 3 spaces. So the first one is we are seeing it right from the first minutes of this topic. So the second one, the green one, is basically a blown up stack, that means the projection of stack. Now because we are discussing heap, the purple region that I have is basically a blown up of this free memory. Okay, so this let us have this function and gradually build to see how we can manipulate the allocation and deallocation of space. So until this point I need not explain. I have integer a which is allocated on the stack, which is a local variable of main. Pointer p, which is a pointer to integer, is also allocated on the stack. Okay, so and that has allocation here. Okay, without worrying much, let us put this statement. P, which is a pointer, I write this line here. Integer star basically specifies it is an integer. This is also called as typecast. So this is pointer to integer. Then I have malloc. Let us not worry too much about it. Then size of int. Let us not worry about this because we are going to see it in much detail. What this malloc does is, this is where we should invoke it. What this malloc does is, it provides the amount of space that is specified within this bracket as a parameter. So here what are you specifying? Size of int, which is 4 bytes. So what this malloc does is, it captures or it provides or it allocates 4 bytes of contiguous location in the heap memory and returns the starting address of it. So what is the starting address of it? This is 500. So that is returned to P. So 500 is basically a pointer to 4 bytes in heap because you asked 4 bytes here, and that pointer, the 500, is now the content of P. Got it? So malloc basically returns the address of the starting address of a block of memory in the heap, The block of memory can be 1 byte, can be 10 bytes, can be 100 bytes, and can run into megabytes based on the applications that you want to run. Okay. Now let's quickly see how to manipulate. Okay. So till this point you know what happened. So integer star malloc. So just bear with me with the splitting of these lines, and then I have star p is equal to 1 1 1 1. So what happened? So p was here, star p is basically 400. So it got assigned to 1 1 1 1 here. And then what did you do? You use the same pointer p, but allocated a different space. So you got another 4 bytes whose starting address is 400. So after the execution of this line, the second malloc statement, the p value is 400. So before that it was 500, and I used that to assign 1111. Now I assign star p to 222. So that's what you get. This is how you manipulate heap memory. So what we have seen so far is how to acquire some space in the heap. But if you remember now, the address 500 we have lost at this point of time. The moment you used p again, reused p again, you have lost the access to this. I don't know what is this block. I don't know what is the address of that block. Though heap is a substantially big memory, and the programmer has liberty of asking whatever space that he wants in memory, memory is a precious resource. Okay. So actually before you reuse the pointer which points to the space in heap, you should see whether that you need the data again. If you don't need that again, there should be a mechanism where you release it, you give it back to the operating system, so that some other program which really wants it may use it. And that's exactly what I specify using red. That's something which is bad. So in technical terms these are called as garbage. If you don't clean the garbage, in C the responsibility of cleaning this up is with the programmer. There are some other nice languages where these things are cleaned up by another process. So that is called as garbage collector. So in C we don't have that. Okay, it is the responsibility of the programmer to clean up that. So the method or the function that will do that is basically the free. Okay, the green line that we have specified, which is after the star p is equal to 111, basically specifies to free this allocation. That means it is provided back to the operating system. So the same block of memory can now be given to some other process. Okay. Now quickly we will discuss. So we have seen how we can manipulate, how we can allocate and deallocate. So malloc allocates, free basically deallocates. So we have seen that. Very quickly we will see the rules of these 4 methods, and we will see probably one more example before we end today's session. So malloc basically returns a pointer to void. If you remember, what did we do? On the right hand side, the first thing we said was int star. So from the void pointer you are converting it to an int pointer. So malloc basically returns a pointer to void, and whatever you specify as a parameter, that many bytes will be returned. Returns a void pointer to a block of memory in heap of size this size. Okay. Return a null value if the memory cannot be allocated. If there are too many processes running, or if the program that you are running has consumed enough of heap memory and the operating system cannot give you any more memory, what you get from a malloc is a null pointer. So before we actually use the space allocated by malloc, it is better to check what did it return. If it returned null, that means the memory is not given to you. Okay. So it is a persistent and will be in memory until the program terminates or the user specifies to release it using a free function. This is persistent. So after you do the malloc, the space is available to you until the program terminates or the user decides to free using the free function. Calloc is a variant of malloc. Okay. You have n elements and then element size. So allocates a region of memory just like malloc. initializes to 0 of n size elements into element size. So, example, if I say character star word calloc 200 size of character, 200 characters are like a block of 200 characters are allocated. Okay, this is size of that 200 characters are allocated, and the starting address of that is returned. The starting address of that is returned. So, similarly, this will return a block of 100 integers, that means 400 bytes. All the bytes will be initialized to 0. Here also it will be initialized to 0. It is just a variant of malloc. If n elements, that is the number of elements, is 0, it returns null, okay, or a pointer to value that can be used to free. Realloc is basically an extension of malloc. Okay. So, what happens is malloc will give you a block of memory, the parameter that you have passed using malloc. When you actually running, the program feels, or the user puts a logic that at this point of time this much memory is not enough, I have to increase its size, okay. So, or decrease its size. So, it resizes the memory region pointed by the pointer size. So, initially if it was pointing to 100 bytes, I can alter this to 200 bytes or 150 bytes or whatever. So, contents are unchanged from the start to the minimum of old and new size. Okay. If the new size is larger than the region added, will be unutilized. If pointer is equal to null, then it is equivalent to malloc. If size is equal to 0, that means this one is equal to 0 and the pointer is not null, then it is equivalent to free. If the area is moved, then a free pointer is done. Let me quickly show this up. If this is the original pointer pointing to, this is the size of that. So, this is size, this is the pointer. What reallocates does is, I can do this. So, what happens is this entire thing remains as it is. The operating system will see that if it can give, if this block is free, it will give the same block, otherwise it will copy and give it. So, it will return a new pointer. Okay. So, this is one case. Suppose if the new region is small, so the space, this thing, that means the contents here and the contents here would remain the same. And there are some special cases, if this pointer is none, if the size is 0, appropriate returns are performed. So, in most of the cases malloc is the function that we use, and sometimes calloc, very rarely we use realloc. So, what is more important, or what you should be more clear, is malloc and free. So, free is a very simple thing, but you should remember that there are some conditions to it. So, it frees the memory space pointed to by pointer. Okay, that does not mean that you can pass any pointer. So, for free to perform its function properly, you need to, the pointer that you pass should be a return value of a previous call to malloc, calloc or realloc, because only then it will be pointing to heap, otherwise it may point to something else which cannot be freed. So, free is a method or a function which can perform only operation or only the operation on the heap. If free pointer has already been called before, undefined behavior occurs. If pointer is null, no operation is performed. Let us quickly see one example now. Okay. So, we have seen a malloc, we will see some example of that. So, this much you already know, a, n and p a are local variables to main, it gets allocated onto the stack. Then you have scanf. So, at this point of time, assume the user key is in 100. Okay. So, that is actually what happens. So, if p a is equal to integer star malloc n into size of int. So, remember this is the dynamic allocation. The size of the block of memory that you want is a function of what the user keys in here. Okay. Malloc n into size of integer. If it is 100, actually the 400 bytes get allocated. So, this is the 400 bytes. The address of that in the heap is 1020. Okay. So, actually here the data should be 1020, there is a small mistake, it is all right. So, star P A is equal to 100, the first location gets now 100, star P A plus 1 is equal to 200. So, that is how you now start and access the heap. So, this malloc will provide you the space of 400 bytes, and you can use the pointers and pointer arithmetic and the star operator to assign the values or to manipulate the values in the heap. So, another way of doing is you can set up a loop and assign it. So, basically this is the loop which will assign the index values to that. So, these values get 0 to 99 because n is 100. I can also use an interactive input. I can say scanf percentage d P A plus A. So, A is initially 0 and goes on from 0 to 99 in steps of 1. So, whatever the user key is in, those 100 values will come and sit here. This is the way you access the heap. Before we wind up, we will see some of these common mistakes that people do. Using a pointer before allocating heap space. So, you see here integer star pointer is equal to 5. In fact, 5 is a constant. Practically no programmer will do this, because normally I told pointers are generally used to point something in the heap. Though in many examples we saw it pointer pointing to another local variable. Sometime during that discussion I did mention that. So, when you already have a direct access, why do you want an indirect access? But we taught that basically to make you understand what pointer is, how do you use pointers to dereference. But people commit the same mistakes. So, they try to assign constants to pointers, they try to assign the stack variables onto the pointers. There is no, it's legally valid, syntactically correct, but you do not get anything by assigning the address of the stack to the pointers. Okay. So, pointers to a large extent will be used to access memory in the heap space. So, changing the pointer, not the value it references. So, integer star pointer, you allocated that. So, pointer is pointer to the space in heap. People say pointer is equal to 10. Okay, sets a value on stack to 10, not value on the heap. So, you should say star pointer. So, this is another common mistake people do. Forgetting to free space on the heap. So, I have star P1 and then probably I use it, and I use star P2, okay, and I say P1 is equal to P2. So, what happens now? P1, the earlier P1 is lost. So, P1 and P2 after the execution of this statement points to the same block in heap, whereas the block of memory which was earlier pointed by pointer P1, there is no way you can access. So, before you actually do this, you should free P1. So, learning to use pointers, you can, at least in the beginning, you try to draw pictures like the way that we have shown. So, when first using pointers, it is much easier to draw pictures to learn what is happening. Remember that a star or an asterisk follows the pointer. Okay, it is an indirect reference. No asterisk refers to the actual pointer variable to the stack. If I say star IP, I am not accessing on the stack. Generally, I am accessing what is pointed by the pointer variable. So, at this point of time, we'll stop. So, in the next session, we will recap the concept of pointers using one or two more examples, especially with characters, before we move on to the next topic. Thank you.